Alright, we got the notes for section 7 of chapter 1. This on truth tables. This is definitely the longest section so far in chapter 1. These notes are probably going to be the longest video so far. Start with the general idea of what is a truth table. We'll start with an extremely easy example of P, Q, and P and Q. And it should be lowercase. My bad. P, Q, P, and Q. Alright, so first up, trying to find in a truth table, we're trying to usually find our rightmost thing, try to figure out when it's true and when it's false for all the values of P, Q, and whatever other statements we have. So first we have to create all the combinations of true and false that we can get. So you got true, 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 false, false, true, and false, false. And so we want to see when this is true for P and Q. So to find P is true and Q is true for this. So well, P true, Q true. This is true here. We have P true, but we don't have Q true, so this is false. Same here, we don't have P true, but we have Q true, so it's false. Down here we don't have P true, and we also don't have Q true, so it's false. So the most general idea is you start with just the basic statements, and then given those statements, given the results of those statements, you can then derive more complicated statements and so on. Let's say we want to derive when is P if and only if Q, or I'll use the different notation with P if and only if Q true. Well, we can use the truth table to figure this out. We have to have our P column for when P is true or false, Q column for when Q is true or false, and then we're going to want to expand out and figure out what else we would need to do to finally have P only if Q, or if P if and only if Q. So we have to figure out what steps go into this, and so the best way to do this is figure out what would an expanded form of P if and only if Q mean. So what this really means, hinted at by the symbol, is P if P then Q, and if Q then P. And this is definitely a more expanded out form. We're dealing with single operationals only and just the biggest forms of all the variables. So this shows us all the parts we need to know. We have to know P and Q so we can derive these, and we have to know each of these so we can then derive this. So we have the P if P then Q column, we'd have the if Q then P column, and then we'd finally have if P then Q and and if Q then P column. So first off, we're going to go back, find all the combinations of true and false for P and Q. The way I like to do this is just go true, true, false, false for P, and true, false for Q, because it gets all of them. So we have if P then Q. If you remember from the previous units, this is true except in this case where P is true and Q is false. So we got true, false, true, true. And then if Q then P, this is true in all statements except where Q is true and P is false. So we've got true, true, false, true. And now we gotta see when is this statement and this statement true? Well, it's gonna be here because they're both true here. It's going to be here because they're both true here. And since they're not both true here, you get false and false. So then I can say, when is it true? It's true when P is true and Q is true, or when P is false and Q is false. So if one of these are held up, then it's going to be, then if and only if is going to hold up. Which gives us like this nice little equality where it shows that P if and only if Q is true when P has the same truth value as Q. So they're both true, they're both false. So it's almost functions, this can almost pseudo function as an equal sign when it comes to logical statements. Then, let's see. Then you also have to be able to figure out different types of opposites. So you got negations, converses, inverses, and contrapositives. Those are the 4 types of negatives we're going to talk about of the statements. So first, we got the negation of sentence. It's very easy. We'll just do this. When P is true, the negation of P is going to be false, and vice versa. So we just got this statement right here. Very simple. But we can't go that simple with converses, inverses, and contrapositives. But first, you might be wondering, what are those? You might forget them for geometry. You might have never learned them. Who knows? So let's go with the simple statement of P, then Q. That's our statement. That means our converse is basically saying the statement backwards. Instead of if P then Q, we're going to go if Q then P. Then for our inverse, we'll go, instead of if P then Q, we'll have not P, if not P, then not Q. So instead of flipping it, we're just negating each of the statements on their own. And then contrapositive is kind of combining it, where we mirror image it type thing, where we go in the opposite direction and we negate everything. So it's not Q, if not Q, then not P. Only one of these is logically equivalent to the statement. I will let you guys think about that for now, and I'll get to it later. And the way we're going to do that is by working each one out from, I guess, top down will work. Let's see if they're true at the same time. If they're true at the same time and false at the same time, then they're equal. So, we gotta go P, Q. So this will be the P. Oh, I should probably start further to the left. This is going to take up a lot of space. So mine will take a second. P, Q, not P, not Q. And I'll get like a little arrow to show what we're trying to figure out is equal to this. At least logically equal. So that yep, and if you're thinking this is a lot of stuff, it is. Your wrist might hurt after doing all of this, but it is what it is, I guess. So first off, we're going to go with our true, true, false, false for our variables over here. True, false for Q. And then we're going to establish not P, not Q, because those are used later on over down here. And this is just the negation. Hopefully you remember how to do this. Just take the opposite truth value. If it's false, then true, true, then false. If P, then Q. You go back, remember, it's only false when P is true and Q is not true. So we're going to go with true, false, true, true. And now remember, this is what we want them to equal. So we want to find the one that's correct. We want to find the one that goes true, false, true, true. If it doesn't go true, false, true, true, that means at least in one circumstance it functions differently logically, which means it is no longer logically equivalent. So if Q, then P, Q is true, P is true, got that. But here we have the issue. If, or I think we have the issue. Oh no, we don't have the issue yet. Q, then P, false, true. Now we have the issue. Sorry about that. So we have Q being true, but P being false. And we know that if the first statement's true and the second one's false, then it's not true. And this down here is true. So I'll get out my red marker of shame. Circle it. This does not match, which means that means that the converse is not logically equivalent to the statement. Next up, we're going to go for the inverse. Not P, then not Q. False, false. So that works here. Not P, then not Q. False, true. This works here. But here you go. True, then false. And same as here. True, then false is just a bunch of problems. Then we got false, false. This is true. So now you're like, well, process of elimination. You're thinking, well, this is going to be the one. Let's see. Not Q, then not P. False, false. That works. Let's see. Yep. We're going to go check something. Contra positive. Not Q, not P. Q. Hold on 1 second. I think I wrote down something wrong on my notes. That's my bad. Give me 1 second. Just true in here. True in here. Yep. Oh wait, that's what I was thinking. Alright, I figured it out. So we got here. Like, oh, we got freaking, if not given true, false. Well, that's, well, dang it, it's false. But, you gotta look. If P, then Q, true, false, true, true. Not Q, then not P, true, false, true, true. So this one works out. Oops, here's next here. One thing that I noticed wasn't brought up in class, but I noticed is that these two, well, these work with each other. These two are both not logically equivalent to the original statement. However, these are logically equivalent to each other, and if you work it out, I'll just do it like up here. Q, then P. The converse of that would be not P, then not Q, which means that these are, in fact, logically equivalent to each other. So we have two sets of logically equivalent statements. Which allows us to now start grouping logical statements that we see much more easily, and that allows us to interchange it. It can definitely make our work look cleaner. We have a cleaner form that we can interchange out for. Because really, like, what looks nicer? If P, then Q, or if not Q, then not P. One of those much cleaner to work with. Then Q, then P is much cleaner than not P, then not Q. Let's see. I guess now we'll just go for one example question. Make sure we got it covered. I'll just take one from the textbook that we're working through. Again, Modern Introductory Analysis by Dolciani, Beckenbach, Jorgensen, Donnelly, and Wooten. So let's look at exercise. Get it back here. Oh, wait, never mind. Before I get to this, there's one more statement I have to teach you, and that is tautology. This means that something's always true. That means that we got our P, Q, and then taut. That means it's always true no matter what. It's a statement that no matter what that, just because of its nature, it could be P or not P or Q or not Q, which means that that's always going to hold up. And so now we can like work out a truth table given something. Let's see. Let's see. All right, this one looks fun. P and the, let's see this. Definitely not an easy one, but definitely manageable, especially with what we've worked on. P, Q, not P, not Q. Alright, got our true, true, false, false, true, false, true, false. And now if you want to pause the video, work through this on your own for a second, I'll let you do it. If you're back, this is how we're going to work through it. First, because we have the not P, not Q we have to find, we're going to work through those. Those are pretty simple. Just take the negation, and then not P and not Q. Go. I'm just looking for the double truths. False, false, false. True. P or Q. Yeah. True, 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 false. And then we're gonna say not P and not Q if and only if P or Q. Well, as we expressed earlier, this is only true when this is will only be true if this is true and this is true, or this is false and this is false. So let's see. These are different here, so false, different here, false, different here, false, different here, false. So we're able to figure out that this statement is false for all combinations of P and Q. That's a pretty clean answer, I think so. I believe that is it for this section. Bye.